And it looks like we're live. So today we're back looking at the Ethereum Codebase for Go-Ethereum, and I want to look at the P2P network a little bit today. So every client that implements Ethereum's protocol, be it Geth or Parity or one of the Python ones or any of the ones that have been made, and Ethereum's gone to like a lot of effort to make lots of clients, they all implement this protocol, so they'll exist on this network, a P2P network, just like our torrents, and they can all talk to each other and they'll all understand what's going on. So I guess everything we've been looking at this point is sort of surrounded by, here is a transaction and that's what's going to go into the blockchain once it gets mined and put into a block. The transaction has to be sent as a message over the network. I mean, it doesn't have to. I guess theoretically, if you wanted to run a node yourself and mine it, you don't have to send it to anyone. But the easiest way for you to get involved in transactions without being a miner is you create the transaction and you send the message over the network, and one of the many miners that are listening will put it in their transaction pool and it will get mined. So this is like, how do each of the clients talk to each other? And there's quite a lot to it. If we look straight away at the peer-to-peer, so we're in the Go-Ethereum Codebase. They've got the peer-to-peer directory, and that's where they're implementing all of this. And they've got quite a lot of code going in here, as well as a heap of like sub ones. And I guess it's too much to go through as one, but I'm going to start with the Message.go, and this message testing file is actually pretty interesting on how it's been implemented. So if we start with this message.test, and these are the tests that they've written to make sure that the code's working. We start with this example message pipe, and they call this pipe function. It returns to them these two items. They send, and this is what they're sending a message to this RW1. They're sending 2, and they're closing number 1. And then afterwards they go into the 2, read the message. This is now in a for loop. Get the message, if the area is not nil, break, put the data into a byte, so decode it into data and print it. And then they reckon it should be output message 8 with zeros, message 5 zeros. So what's happening here? If we go into this message, they start straight away by defining the message structure. And here is a payload, which is what's getting sent over it. And they mention here that it's it's encoded. The payload is encoded in ROP, which is their normal data encoding format. And we say here that if you want to send anything, you have to make a new message. So a message is used every single time. If we look at here, this is a little bit higher level because this send function is creating the message. And what this pipe is doing is it's opening up two sides that are connected. So it's abstracting away all the peer-to-peer stuff at the moment. They're just saying that here's a reader, here's a writer. It's like if you write to a file, then open up and read from that file. It's very similar to that, but instead of being a file, it's a network protocol, and there's two sides of it, one person who's reading and one person who's writing. And RW means the pipe can read and write. So back here, it's also got a code, which I'm not sure what the code's for at this point. But in this case, they're sending the code as an 8 for byte code, a byte array of zeros, and then they send another one with a code of 5 and 2 byte arrays. It's an array of bytes, 1 and 1. And what's coming back is the message, put in the code here, comma, the data. So code message 8, data 0, code message 5, that. So this message has got the code and the payload saved here. Size is obviously for just when they're communicating, you need to know how much is being sent over it, and then they put in a timestamp on it. They put in a decode function here, which is what we're looking at here. So they get the message, they got their read writer, reads a message, you got the message, you can decode it into a blank byte array. So what's happening here? Decode. It's opening up a new RLP decoder. They're passing in the payload and the size of the payload to this RLP library that's able to read a byte array in RLP and decode it. And it's super just wrapping this function. So the decode message is actually just going into the payload and decoding the payload, which is an RLP string. So this really just handballs it down to the next library, which is the RLP library, which we will need to go through at some point. They get a string message, and they're just literally dumping the bytes and the no, it doesn't actually tell you the byte code. It just says the code and the size. So the size must be in bytes. Cool. Literally does nothing still. Discard. Discard reads any remaining payload data into black hole. So because it's a read writer, you can partially read like 2 bytes out of 10 if you want. Here it's saying you can discard the remaining ones. Again, useful. These are just utility functions for when you get the message. You're going to want to be able to read it, you're going to be able to write it, and it's the payload in there you really care about. Here, they have a message reader, which all it is saying that for something to be a message reader, it just has to have the function read message. And that read message function should return a message and the error handling stuff. The opposite side of it is the writer, which is the same thing at this point. It's just defining that this interface just has to be something that writes a message. You can take that as a function and pass it a message, and it gives you an error back. And this message read writer just says that something's got both of these. Then it's a message read writer interface. And if we look up here, when it's making the pipes. It says there's a send one. I don't want to go into that just yet. I want to pull up the pipe maker, which we were looking at before. So message pipe creates a pipe. So the two sides of the messaging system. And you could probably just think of it as like, if you've got a cup on a string, you got two cups on each side, and you can talk to each other. It's like making that pipe, and each one of these is a cup. You can talk in this one, and it comes out that one. You can talk in that one, and it comes out that one. Full duplex, both ends implement message read writer. So message read writer is this interface that they were talking about up here. And all that's saying is it just has the ability, a reader and writer, to both read a message. So you can got the writer, you can go writer.read message, and you also go writer.write message. That's all it is at this point. It's something that gives you those functions. So this pipe takes no arguments and returns you two of these items, and with them you can call both a writing and a reading function on them. It hasn't told you how it's implemented these yet, but it's just making them for you. So RW1, RW2, read write 1, read write 2, ampersand message pipe read 1, passing C1, C2, closing, closed. So this message pipe read write, message pipe read write. There you go. Here's the structure. So, super fun. W, I guess, is write. R, I guess, is read. They seem pretty reasonable. Closing, closed. Closed is an integer. So these are channels. Now, unfortunately, I don't know channels super well. I'm still relatively new to Go. Now, they connect concurrent Go routines. So you can send values into a channel from one routine and receive them in another one. So this GoFunc opens up another Go routine in a separate process, and that's so you can run them side by side and they're faster on multiple cores. And when you want to talk between them, that's what these channels are for. So in this situation, you've got a channel that you can put a message into, and this one is that you take a message out of it, and that message structure is exactly what's up there before. They're not the closing and close are useful yet. So you've got this structure, and it's implementing the write message, which, if we've seen up a little bit before, in this message writer, therefore it satisfies this message writer interface. Next. Very good. So you got this message pipe read write structure. It's got the write message function, and I imagine just here it's got a read message. So it implements both of the functions needed to be part of that implementation. Which it wants here. So, what happens when you write a message? This is it checking if the pipe has been closed. So that's going to be a yes or no. If it's 0, it's closed. No, if it's 1, it's closed. If it's closed, true. Then it won't do anything. You can't write a message until closed. So if that's set as 1, close it. So I'm assuming down below there's a function that says close. And all that does is adds integer 32 to p closed. So you add 1 to the integer. No, you store the integer. Yeah, okay, so what if it's testing if you've got 0 in here? And the way it's doing it is saying it's if I add 1 to this guy here, and it does not equal 1, then it's already closed, because it's 0, so it says if 0. I'm not sure why. I'm sure it's very actually smart why they're doing it. If it isn't, and you've called it closed, it puts 1 into that closed. And then it closes the closing, which is the channel itself. Cool. So you make sure it's not closed by checking that not binary structure. Consumed. You make the channel structure. You get the payload, ampersand end of file signal, which takes up the payload, a message size, and consumed. So this write message. So the message has those two, payload in that, and then it formats that into this consumed. So it makes a channel. So this is like a writer, but for channels, and you can put it in there. And then we make the payload. We put into P.W. So we put the message into the writer channel. If the size is greater than 0, then we wait for it to be read or discarded. Cool. So it just looks like they're putting into the channel. All they're doing is formatting it in that is end of file signal, which is going to be below in this this file, I believe. We'll get to it in a little bit. Makes the message.payload, chucks that into the writer. And then it does an infinite loop here. And if the other side reads it, or if the other side closes it, or someone else closes it, return nil. So this case you put that in here. if it's closing, then they won't look at it. Okay, that's really straightforward. All they're doing is taking this message, structuring it, sending it, waiting for it to be consumed by the other side. And if they don't read it, then it gives you an error. And then we expect this other side to read it. So they check again if that p dot closed is 0. If it's not closed, which is, yeah, okay, easy enough saying, right? They get the message out of that p dot reader. And I guess the key here, returning the message, is that when this message read write structure is being made, and it's being made here, there's two channels being made here, and they're swapping them around because they're saying one is the receiver, one is the sender. So now that they're both the same, you've got two read-write structures, and they're both linked. Calling the reader, calling the writer. And this so far is all really low-level stuff. And they've just given the people the next level up the ability to send a message that has some form of code and a payload that's encoded in this ROP content. If I go back up, because they're going to look into the send functions that we kind of, there's the end of file signal structure, which we're looking at say. Send, cool. So in this message test, we looked at example message. They call this pipe, get the two read writers that are linked, send a message, send another message down this one, look on the other side, see it get received, loops, gives them data, they print it. This send function is now going to be what we're looking at, and they're going to go through these functions that were available from this message pipe read writer, this write message and read writer. So the send's just going to call this write message, and it's going to format some data into a new message structure, I would assume. And it's probably not going to be too complex, because at this point it's just like boilerplate, generic boilerplate to make something that can communicate between two items over a channel. And this is going to be TCP, so it's just sent almost the same way as a website would be. Like when a website communicates, all it does is it sends a message over just, it's literally less like Morse code. You've got two computers that have the ability to type Morse code at each other really quickly, and it's just how do you structure the hellos and sign-offs and stuff is done in a special way, which is TCP, and you give them certain numbers, so if you want to differentiate between who you're talking to, and that's where ports and stuff come in, and that's all they're doing here. They're doing something exactly the same as that. They're giving a code, which I imagine is like, I can't even say it, but like if you have like a hello protocol, and all it does is you've got all your peers, and you want to join, is you send a hello out, and someone will reply back with, what do they call it in here? They say hello and their status message, and the status includes the total difficulty and hash of their best block. So you say hello, the other one says hello back, but you send how much, what your blockchain is looking like at the moment, and the person with the worst one asks to see the full one, and then if it seems legit, they'll sync each other up. So it's really like, it's not at that level yet, but these guys, what they're doing is they're putting in the basic messages you can send, and then the hello message is going to be defined somewhere in one of these other ones. I wonder if we can find RLPX. Is it going to have a hello? No. Right message. Because all these do is they got, nah, this is another layer already. This is a transport protocol used by the actual connections. What do they do? Dial, message, metrics, protocols. Discovery. I reckon someone in here, it's going to be it. Simulate, run, test. Is it going to be a hello? No. Bugger. We'll find out in a little bit. All that's saying is they send a hello message. Is the first thing you do when you want to sync your blockchain. You send hello to everyone on the chain, or a couple of people, and you find out what is the total difficulty, which is just, that was actually encoded in a block. We looked at that the other day. So each block has the total difficulty saved in it, which is just a cumulative difficulty of their best block. So the newest block that they've got, they send that, and whoever has the lowest obviously has the oldest chain, and it needs to be updated. Cool. Anyway, back to messages. The very bottom line. Read message, send message, write message. Now we're going back up to send, because this guy said send, and he is sent, takes the writer, takes the status code, takes the payload. So it's really going to be just like, take that, call another message. Here we go. Message writer, message code, data. RLP encode to reader data, which returns a size, a reader, and an error. If there's no error, we call the write message. Super fucking complicated. Message code. Takes that message code, dumps it in this new message structure. Size is what gets out here. Payload. Just R, so this RLP encode to reader. RLP is sort of getting important. It keeps coming up. I think I need to look at that next. Not today, but like tomorrow probably. Send items. Elms. So this just gives the option to, you can pass in an array here. That's what these dots are, is there can be more than one parameter. And then this is going to iterate through it. No, this chucks it as an array and then calls that once with all these elements as an array. This is probably what's going to say here. Send items writes an RLP with the given code. So give the code. I still don't know why they use this code. What are they going to be used for? Who knows? We'll find that out. EOF signal. End of file signal. And the end of final channel is closed when the wrapper reader returns an error or when the count bytes have been read. Cool, so this is all really low level. You make a channel and then you send a message down a channel. If we Google like how to make peer-to-peer network. It's literally, no, that's not it. So, how do you make Bone Dapster? Wolfgang. Wolfgang. He's got 3 golds. I don't know how he has 3. How do you go creating the next BitTorrent? Isn't this idiot's replied with, it is very hard to make. Like, why are you answering if it's very hard to make? Anyway, so in one of these, building a P2P system, you know, and these are like tutorials on how to make it. These are really looking by generic. Choose your programming language. Step 1, choose your programming language. Step 2, make it. That's all there is, 2-step process. Anyway, so generic tutorials on how to make a peer-to-peer network exist, and they literally start off with sending messages between peers, which is this. Yeah, you close the channel, expect a message, and this is probably just going to be a callback or something that just says without even looking at it. If you've got a reader, keep reading it until something comes back. But this one expects a code, so you tell it you're waiting for an 8 code or a 5 code. Expected, unexpected, unexpected. No, they don't test it here, unfortunately. Message eventer wraps the reader and writer and sends events whenever a message is sent or received. So this is when you've got in your program, you implement these events that you can listen to, and you make callbacks. So someone sends a message, it means you can have something else waiting for that message to come in. Read message eventer. So this is just the next level up. So what did the T, because there's going to be quite a few layers they're building on here. What did the RLPX implement? They had an RLPX frame read write. RLPX frame read write. No, go back. Let it go. Next. So this implements a read writer, and that's about it. So the new frame, this encodes it. So this is even go as far as putting in a encryption layer on this. Or it might just be a signature, who knows at this point. So you got a connection and you write a message. And here's our message structure. Encoding the message to bytes. P-type. Protocol type. Maybe. Who knows? So, I actually reckon that all this pipe stuff they're doing here is simply between threads in your CPU. Creates a message pipe. And all this stuff here, you can write into a pipe and read into a pipe, is so that you can talk between processes. If you've got several processes running, I guess if you're running like several nodes on the same computer, like your own private network, and they were all talking with this would be easier. Because I don't think this is actually, if I go up at the top, they don't actually implement any real network protocols or frameworks or anything, because it's all doing over these channels. And if we look at this channel, I was expecting it to import this net, but they don't. These channels that connect concurrent Go routines, which is between threads in a CPU. And then they got these events, which makes it sound like when you've got like a process sets up events, which you'd almost think that was the same program listening to its own events that it's emitting. So the key thing that kind of comes out of here is that all these read-write functions aren't called when you talk between two peers. It's when you talk between two processes that are sending messages to each other, which is interesting because that means it's that general when you're talking between the different, if you're running 2 or 3 nodes on your computer, or if you're running, I'm not even sure yet at this point. And then they've got it so you got some events that it just gives you callbacks when you send and receive stuff. It can be like, there is a new message, and then you call your function that actually reads that message. And the key thing that kind of comes out of it is this message structure. This actually is used by the real RLP. Because here, an ROP frame and that'll be what is actually sent between the clients. Ethereum network architecture analysis. Interesting. R-loop token. Yeah, no, that's the wrong. You run your Geth, start up a node, which is a full node, so it has to sync it. Init main go, command Geth go. Ooh, Geth calls make a full node, and starts the node. Service. So that's where all the servers listening. Golang P2P communication link. ETH protocol light Ethereum server. Supports multiple protocols. communication layer. Ethereum uses PLPX encode, shared key encryption, read-write frame processor, Go.net. Yeah, okay, so they're looking at server 1 here. The server starts listening, blah, blah, blah. Message processing. So you quit, run peer, read loop, run, no. Interaction progress. Protocols. Share key. There we go. Read write frame. After you generate a shared key, so you do your encryption handshakes, so you know what secret code the two computers are going to talk to each other with. After you've made that and generated the code, the frame is initialized. The purpose of this is to support the multiplex protocol of every single connection. Combining with this, I think that's what I had earlier. The frame has a header, a MAC frame. Where'd the above code go? Write message. So a new ROP frame has a connection, ingress, outgress, write message, and you pass a message to it, encodes it as ROP, encodes the code as an ROP. This is if you want to talk quicker without verifying the messages and stuff. They're building in all these sort of functions to make it quick. I don't want to drive into that right now. Make a header buff. Is that in here? No. You get the protocol type, the length plus the message size, the frame size. If the frame size is greater than 24 bit integer, otherwise you put it in the head buff. So you put the size of the message into the buffer. You copy the 0 header. So they got a blank 0 header here. 0 header. Use this in place of actual frame data. Replace this when message code contains a protocol. Cool, snore. So they write the size of what's going to go into it, and they make this frame. They write the size. They ignore the first 3 bytes because that's obviously what 24 bits is. And they put a 0, an empty header in there. And then read, write, encode XOR keystring. So their first half is now encrypted. So the first 3, what's the next 13, are encrypted. 0 header 80. So that just is all them, I think. 1, 2, 3, 4, 5, and 0 bytes. Yeah, cool. So I don't know what that header looks like. I guess that's going to be in this header. Dev P2P transcript header. handshake framing, they put in an auth frame, has a header, a MAC frame data, and a frame MAC. Signature. The header is the frame size, the header data, and the padding. What's in header data? They've got a list of the protocol types. I think you define these protocol types. Is an integer. Ooh, here we go. So an integer that's less than the biggest 16-bit integer, big endian. So that's what the numbers are going to be used for. So your header just says this is the list of protocols. Padding is 0 fills. Frame content is any binary data. Cool. You write the encrypted frame. Stream writer. You write encoder. Blah. So they write the frame. Egress MAC. So the signature, I guess. And then they read out of it. So this is where the actual communication between peers is going to be, and that's where it's pulling in this net library, which I expected earlier. Didn't see. Because yeah, this RLPX frame is what gets put into this upper one here somewhere. Yeah, where is it? This RLPX structure. So they got a connection here. They got a frame, and they're going to write that frame over that network at some point. So the RLPX write message. Write message to the frame. But I guess the key that comes out of it is they are writing these message, which is what this file has been talking about, and that's all that's really coming out of this. This is the only important thing out of this file. And then the high levels use that message. And I might call it there for today. Because this is quite a big library. But all it seems to be doing is making this. I kind of want to go through this a bit deeper before. Understanding how the handshake works, and there's this RLPX frame. It's got a header MAC. It's the left 16 of egress MAC. So it's a signature. The bytes that are going out over the reader consistently added. And it's doing left 16 of those. So it's just a signature. Any authentication is consistently being updated to prove that that's the person sending it, I believe. I need to go through this a bit deeper. Cool. So what we've seen today is that this message structure, very, very simple. All it is a code, it's an integer, a payload, which is a bunch of bytes encoded as RLP, and then this RLPX frame sends and receives it. And then clear. If we have a look at server, what it will do is it will start listening for, this is implementing all the private keys and stuff. This is a big file. It's going to be a key one to go through. Like as important as blockchain probably. Config with all the private keys and stuff, and the addresses they are actually going to use to form the connection. And then, yeah, that's the connection. RLPX. They got new RLPX. When you start it up, they create a new RLPX. New transport. Next. Got handshake. Listener. That's if you're listening. What about dial? .go. Slash RLPX. Not in here at all. This is the opposite side. This is them connecting to a server if you want to. Once you've got a server running, then you'll have the ability to have RLPX, which is not the failed handshake, which will be this new transport. So the server has a new transport. And that is where you have the ability to send your RLPX. That's where you. I'm not sure about that yet. RLPX.go, and that's where you'll be able to call to send messages and stuff. So, yeah. Anyway, I'm going to leave it at that today. It's protocol access. Have a look. Cap. Nothing exciting. Peer.go. We'll have. Ooh, there's a handshake. Hello? Hello. Is that going to be in here? No, bugger. Want to know where that hello? Peer events. New peer. ID, node, name, cap, return address, reliable address, disconnect, string. New peer, blah, run. Ooh, what's run say? Write structure. Write start. Ping message, read message, read loop. Handle message, here we go. So you got your peers. So your server gives you a list of peers, I imagine. And handle message. If it's a ping message, discard. So discard message. Less than protocol left, discard. Sub-protocol message, it's out of range. Match protocols. Or so this is where they test to make sure that the two peers have the same protocols available to listen, and if it's protocol message doesn't exist, then it will delete it. If it finds a protocol responsible for handling, so you set up a handler. So you define a protocol and you define a process that can read and handle messages from that protocol. And if it gets a message to it, it sends that data structure to this function. So it finds the handler. Cool. That's very good. I'm going to look at that later. Anyway, I'm going to leave it there. Thanks guys. I'll catch you tomorrow and I will talk about probably this some more because this actually got a bit interesting. Anyway, take care.